All right, so here we have section 12.1, the start of three-dimensional figures. Today we're focusing on polyhedrons. And a polyhedron is a solid that's bounded by polygons called faces that enclose a single region of space. So it's a three-dimensional solid figure, and all of the sides that you can see are actual polygons. So squares, rectangles, triangles, things such as that make up the faces. An edge is going to be a line segment formed by the intersection of two faces. So where two of those polygons come together and meet, they're going to make an edge. And then the vertex in a polyhedron is going to be a point where three or more edges meet. So basically an edge is two faces or two sides coming together. Vertex is three edges coming together. In this picture we have multiple different versions of three-dimensional figures. Can't really see them very well on your notes. It didn't print out very well, but on here you can see it a little bit better. And we want to determine which of those solids above would be considered a polyhedron. And remember, a polyhedron is made up of polygon faces. So it's got to have a square, rectangle, triangle, hexagon, something like that, making up the faces. And when we learned about polygons, we learned that anything that had a curve in it was not a polygon. So same kind of rule here with these polyhedron. Anything that has a curve to it is not going to be a polyhedron because it can't be a polygon face if it's got a curve to it. So that allows us to cancel out several of these real quick. Sphere, the ovoid, and the ellipsoid, and then also the cylinder and the cone, which have circles in them. We will come back and look at a sphere, cone, and cylinder later on in the chapter, but for right now they don't fit the rule for polyhedron. And so we have 5 figures left that would be polyhedrons. So first one is a cube, and I'm going to highlight it here a little bit so we can see a little bit better how it's made up. So in a cube you have, as far as faces go, you have a square at the top and the bottom, and then 4 going around the sides. That's going to be 6 faces. Vertices, we have 4 on the top and then 4 on the bottom down there, so that'll be 8 vertices. And then edges are anywhere where the two sides come together, so we have 1, 2, 3, 4 on the top, 4 on the bottom, and then around the sides we have 4, so that's going to be 12. The next one we have is a triangular based pyramid. And so if I'm looking at it, like that. So as far as faces, you got a triangle on the bottom and 3 triangles going around the sides, so that's going to be 4 faces. Vertices, you got 1, 2, 3 on the base, and then 1 at the top where the 3 triangles come together, so 4 vertices. And then edges, you have 3 at the base, and then 1, 2, 3 going around the side, so 6 the number of edges. Right. We have a rectangular prism. So rectangular prism. So and so really a rectangular prism is just like a cube, except for it's got rectangles instead of squares on some of the faces. So all the numbers, though, are going to be the same. So the 6 faces, 8 vertices, and 12 edges. Next one, we got a triangular prism. And so the triangular prism is made up of basically 2 triangles and then 3 rectangles. So 2 and 3, so give us 5 faces. For vertices, we got 1, 2, 3, and 1, 2, 3, so 6 vertices. And then edges, we got 1, 2, 3 edges, 1, 2, 3, 1, 2, 3. 3 on each triangle, and 3 going around the sides. So that'll be 9. And the last polyhedron in the picture is a square-based pyramid. In the square-based pyramid, we have a square for the base. And then 4 triangles going around the sides, so it's going to be 5 faces. For the vertices, we got 1, 2, 3, 4 on the bottom, and 1 at the top, so 5 vertices. And then the edges, we got 1, 2, 3, 4 on the top, or on the sides, and 1, 2, 3, 4 on the bottom, so 8. So when we look at the polyhedrons, we can have a regular polyhedron, which is going to require that all the faces are congruent regular polygons. So remember, a regular polygon is a polygon that's equilateral and equiangular, or in other words, all the sides are the same length, all the angles are the same. So like a square, equilateral triangle, a regular octagon like a stop sign, that kind of stuff would be regular polygons that would have to be the faces of a regular polyhedron. And all those have to be the same polygon. So it has, if one square, they all have to be squares. If one of them is a triangle, they all have to be triangles. And they all have to be congruent. All right. For a convex polyhedron, it's going to be a polyhedron which any 2 points on its surface can be connected by a segment that lies entirely inside the polyhedron. So if I connect one face to another face with 2 points, that line, that segment is going to be completely inside the figure if it's convex. And if it's concave, a polyhedron in which a line connecting 2 points on its surface goes outside the polyhedron. So basically, if there are any 2 points on the sides or on the faces that you can connect with a line that goes outside the polyhedron, it's going to be concave. If you can't figure out a way to draw a line segment that connects 2 points and goes outside, then it's got to be convex. So we've got a couple of examples here, A and B. Both of them are a decahedron, which means that it has 10 faces. And so we want to know if they are convex first off. So figure A, we've got this one line that it's showing in here that's connecting the top to the bottom, and it's in the inside. Really, if I try to connect any 2 points anywhere else, the segment that would connect those 2 points is going to be inside the figure. So that makes that one convex. On B here, though, I've got a line that I can see is connecting 2 sides, 2 faces, and it is not inside the polyhedron. So since you can connect 2 points and go outside the polyhedron, that means that that one is concave. And then the next question asks if they're regular. So we want to look at each face and see if they're all equilateral, equiangular, and all congruent. So if I look at figure A, we've got a bunch of trapezoids making up the side or the faces with one congruence mark there. But just being a trapezoid, we should know that all the sides are not going to be congruent in length with the trapezoid. So the trapezoids are not regular. Plus another thing to notice is that we've got a bunch of trapezoids, but the top and bottom are squares. So you got two different shapes, so that automatically discounts it and keeps it from being regular. So this one's not regular. And then for B, when we look at this figure, almost every side is a different shape. Right? So just by looking at that one almost right off, you should be able to tell that it's not regular. All right, so then the next thing talks about cross sections, which is basically the intersection of a plane and a solid. And what we see when we look at cross sections looks kind of like a piece of paper slicing through a solid object. Right? And so depending on at what angle that plane cuts through, we can get different shapes of cross sections. So if we look at this first one, we have got a rectangular prism being cut straight through horizontally. And so the shape that's formed in figure 1 would be a square. Figure 2, the plane is cutting through vertically, straight through it vertically. And so that one is going to give us a rectangle for the cross section. And there are other shapes that can be created depending on what angle you cut it at. Like I could have a plane that cuts through and just kind of cuts the corner off there. And then we could see that we have a triangle shape there. All right, so all depends on what angle that cross section or what angle that plane cuts through the solid to see what shape we create. All right, so we've got Platonic solids, and these are all going to be regular convex polyhedron. All right, you've got a regular tetrahedron. Tetra is 4, so we have 4 faces, which is this figure down here, which is really a pyramid, a triangular based pyramid. All the triangles, though, are going to be equilateral, equiangular triangles. You got a cube, or the fancy name for it is a hexahedron. Hex for 6. So 6 faces, and all faces are going to be squares, which are regular polygons. You can have a regular octahedron, which is 8 faces. So it's like 2 square-based pyramids being put together at the base. All the faces are going to be equilateral, equiangular triangles. You have a regular dodecahedron, which is 12 faces. And this one, all the faces are regular pentagons. If you've ever played Dungeons and Dragons, they have a 12-sided dice that you use. And so that would be a dodecahedron if you've ever played Dungeons and Dragons, if you're that cool. All right, so then a regular icosahedron, it's going to have 20 faces, all of which are equilateral, equiangular triangles. The more faces you start putting together, you start seeing that it starts looking more like a sphere and less like a polyhedron in some cases. All right, so Euler's theorem says the number of faces, F, vertices, V, and edges, E, of a polyhedron are related by the formula F plus V equals E plus 2. So the number of faces plus the number of vertices is going to be equal to the number of edges plus 2. So we've got a solid that has 10 faces. 4 triangles, 1 square, 4 hexagons, and 1 octagon. How many vertices does the solid have? And so, first off, we know that the F value, the number of faces, is 10. And then, when you look at all of these things that go together to make this polyhedron, you gotta hope that there's another way to figure out how many edges there are without drawing it, right? And so, for the E, that's going to be number of edges, which basically, to figure out the number of edges, since they didn't tell us how many edges, we take the number of sides and divide by 2, because that's where one side from one polygon is going to come together with a side of another polygon. So 2 sides will make 1 edge. And so to figure out the total number of sides, look at all the shapes that we have. We have 4 triangles. So that's 4. And a triangle has 3 sides. So 4 times 3, 12. You have 1 square. So 1 times 4 is 4. 4 hexagons. A hexagon has how many sides? 6. Yep. Which is 4 times 6 is 24. 1 octagon, 1 times 8 is 8. So we add all of those together. 12 plus 4 is 16, plus 24 is 40, plus 8 is 48 sides total. So the number of edges is going to be 48 divided by 2, or 24. So now we have 2 of the variables. So we should be able to solve for the third one, which is the number of vertices. Using that formula, F plus V equals E plus 2. So F is 10. V is what we're trying to figure out. E is 24. And plus 2. So once we have it set up here, it's a pretty simple algebra problem to solve. So we have 10 plus V and equal 26, and subtract 10 from both sides. The number of our vertices is going to be 16. Alright, so the next one says some quartz crystals are pointed on both ends and have 14 vertices and 30 edges. How many faces would the crystal have? So this one's actually a little easier than the last one because it straight up gives us how many vertices and edges. So we've got the V, which is going to be 14. E is 30. And we're trying to solve for F. So still using Euler's formula. F plus V equals E plus 2. So F plus V, which is 14, is going to equal E, which is 30, plus 2. So F plus 14 will equal 32. Subtract 14 from both sides, and our F will be 18. So 18 faces in that quartz crystal. The last one says a...
Can you please send Melanie to the office?
Alright, so a paper model of a geodesic dome is composed of 180 triangular faces. How many vertices does it have? So we know the faces, F is 180. We're trying to find vertices. And so that means that edges should be able to, we should be able to come up with the edges, right? Which is the number of sides divided by 2. So the number of sides, we're going to get that by taking 180 times 3 for triangle, be 540. So 540 divided by 2 will give us 270 edges. And so now we can plug the F and the E into the equation. So F plus B equals E plus 2. So F is 180 plus B equals E, which is 270, plus 2. 180 plus B equals 272. Subtract the 180 from both sides. And we're going to have 92 vertices in that figure. Right. And a geodesic dome, it's kind of like at Epcot Center at Disney World. You've seen the big white globe thing they have out there in the middle. And so it probably has more than 92 vertices. All right, so that completes the note.